This session was advertised as Java in containers, but I changed the title to JVM in containers, because at the end of the day, what really matters is the Java virtual machine that runs in the container. The JVM only understands bytecode. Most of the time, that bytecode comes from the Delabassee compiler, but if it comes from something else, it doesn't matter. So my name is Delabassee. Despite my French accent, I'm not French. I live on in the French-speaking side of Belgium, where I work for Oracle in the Java platform group. So I'm remote. You can find me on Twitter at Delabassee. The Java platform group is basically the organization within Oracle that is responsible for the Java platform and for OpenJDK. So this is a Java track. So there is a pattern. You need two things. The first one is a Duke. And the second one, anybody can guess what is the second thing that you need in the Java track? A safe harbor statement slide. So this is the Oracle one. I'm a bit jealous because Ben has a very long one, so we only have a short one, so sorry for that. This is my personal disclaimer. So if you have been following the news, Apple has released a few months ago a new MacBook Pro with a keyboard that works. Well, unfortunately, I still have the old one. So if today any of my demo fails, it's not my fault, it's the keyboard. Not only that, this is also a subtle message for my manager. OK, let's discuss JVM and Java. So this year is an important year for Java because we're about to celebrate the 25 years anniversary of Java. So since 25 years, Java has been developed and has evolved. And that evolution is basically based on two core principles. The first one is developer productivity. So it has to be easy to write code, but writing code is only one part of the story. Maintainability is also very important. So that's why it's also very important to be able to easily write and read the code that has been produced. So that's one of the pillars of the evolution of Java. The second one is application performance. So over the years, we have enhanced the platform to make sure that your code runs in a very efficient manner. So we have improved the GC that were present in the early days of the platform. We have added new ones, such as G1, ZGC. We have a JIT compiler that allows us to, well, that allows the Java virtual machine to do on-the-fly optimization, and so on and so on. So that evolution over the last 25 years has been done based on those two pillars, keeping in mind that the world around is also evolving. There are new programming paradigms that are appearing or that are getting more popular, so Java has to make sure to cope with the right ones. Lambda expression introduced in 8 are a good example of that. Application style. 20 years ago, we were mainly writing monoliths. Those days, it's all about microservices and function as a services. Obviously, the platform is able to cope with that as well. The hardware that we run our code on is also evolving a lot. We have more CPUs, more cores. Each CPU have multi-level cache, and so on and so on. So the platform, the JVM, has also be able to cope with that. And last but not least, deployment style are also evolving. 15 years ago, we were deploying monoliths. If we were agile, we were deploying once or twice a year into our own data centers. Those days, with CI/CD, we were basically doing multiple deployments a day into containers that are deployed in a Kubernetes cluster in the cloud, right? So, containers. How many of you are using containers today? OK, that's what I guess. So I don't have to spend too much time on containers. So basically, a container is a standard way of packaging a software with its dependency. There are multiple runtimes, Docker, Cryo, LXC, and so on and so on. At the end of the day, what I'm going to discuss today apply to any OCI-compliant containers that is based on namespace and C groups. So namespace and C groups are a Linux kernel's technology that basically give us the ability to create containers. I'm going to use Docker, but just because I'm used to that, it would also work on Podman or any other runtime. So containers shouldn't be confused with virtual machine. On one hand, we have containers that are super lightweight. Starting a container takes a few milliseconds. Well, depending on the case, but the startup time of a container can be pretty fast. The thing with container is that they're relying on some facilities of the underlying Linux kernel, namespace, C group, union file systems, to basically give us this idea that our code runs isolated. But it's not really isolated, because at the end of the day, our containers rely on the underlying kernel host to run the code. So that basically means that we are running on the same operating system that we have on the host. On the other hand, we have a virtual machine that provides us real isolation. The thing with VM is that they're very expensive. Starting a VM is a costly operation, so you don't want to do that too many times. On the other hand, starting a container and killing a container is almost instantaneously. So you can do that. You can do that as many times as you want. Container can become ephemeral if you want. So with VM, we have a strong isolation, but it comes at a cost. With container, we don't have that cost, but we don't have a very good isolation. So in between, we have what now Kata containers, which basically rely on a lightweight VM to basically provide the benefit of both worlds. So we have the isolation of VM with basically the cost and the startup time that we can reach on the container side. So Java and the GVM. If we look at the GVM container landscape, I think that we're pretty lucky because it's hard those days to find a modern framework that doesn't support out-of-the-box containers. So if you're using Elidon, Micronaut, Gypters, and so on, you can directly create a containerized version of your application. On the tooling side, we have a Maven plugin. We have the ability to use Jib, so to create containers using Jib directly from Maven. The IDE, if you take IntelliJ, for example, it supports out of the box the ability to directly create container image, and so on and so on. So if we look on the GVM container landscape, well, it's pretty solid. Now, the first thing that I would like to discuss is GVM container awareness. So since Java 8, we have invested in the GVM to make sure that it runs nicely whenever that GVM runs within the containers. There are multiple reasons for that, such as good resource usage. But one important reason is what we call the GVM ergonomics. So GVM ergonomics is basically something that has been added in Java 8, I believe. And it's the ability for the GVM, when it runs, so it's the ability for the GVM to basically provide a default behavior that works. So the GVM, if you don't tune the GVM, will provide you decent behavior. The GVM will look at few metrics, like the number of CPUs, how much memory does it have, and based on that, it will infer some configuration, such as what heap size should I use, and so on and so on. So to illustrate that, I have a demo. So let's see. First, I'm going to SSH to a VM in the cloud. So let's see. So what I have here, I have a simple hello world application that basically look at how many CPU it has, what is the memory, and so on and so on. So some basic metrics. What is the GVM vendors, and so on. So we can run that. So Java hello world.java. So I'm not compiling the class, I'm directly running it against Java. So it's a JDK 1302, the vendor is Oracle, it has 4 CPU, and so on and so on. Right? So the three that you see there is the command for join pool threads, which are configured based on the number of CPU. So given that we have 4 CPU, we have 3 threads for the command for join pool. Right? So next I'm going to Dockerize that code. So for that I have a super slow laptop. Let's pretend it's the keyboard. So this is my Dockerfile, so it's pretty basic. I take a Java base image, I create a directory, I copy the source, I Java-C, so I compile that source, and then I run that. So Docker build. -t, qcon, and this is the context. Okay, so let's run that. So the image is qcon. So you see this code is running within my container. So the GVM, the Java version is different. It's an older one. It runs inside a container. Yes, it has 4 cores. So the command for join pool is set to 3. If I look at the number of CPU that my VM has, it has 4 CPU, so that match. Now, what I'm going to do next, I'm going to run the same code, but I'm going to limit the resources that my container can use. Now, this time, instead of 4 CPU, my container will only be able to use 2. And, well, you see that this time, the code inside, the GVM inside still sees 4 cores. So all the ergonomics will be based on that false assumption. You see that in terms of memory, it has like 3 gigabytes. So what I can do, I can limit that memory, let's say to 256 megabytes. Yeah, this is, you're not on stage. So don't complain. Maybe it's the network. So 266 megabytes, and you see that my GVM still see more than that, and it still see the 4 CPU. So something is wrong. Why? Well, simply because of that. So if I look at the Dockerfile, I'm using this Java latest image, which is completely outdated. So I need to fix that. So I'm going to simply switch to OpenJDK latest. So let's build the image again. And let's run the image again with the limitation that we set, like 3 CPU and 266 megabytes. And you see that this time the GVM sees 3 CPU, so the command for join pool will be configured with 2 threads, which makes sense. And the runtime memory is below what the GVM sees. I mean, there is a formula that calculates that. But this time, we can be sure that our code running in that container will not be killed by the container engine. In the previous case, we can be sure that given that our Java code was, well, the GVM was seeing 4 CPU and was also seeing more memory that it has access to, that pretty rapidly the GVM will be killed by the container engine because it will basically try to overconsume the resources that are available. So that's why using a GVM that is container aware is important. Okay, let's talk about performance. So something I didn't show you in the previous example is that the generated image, so the Docker image generated, was pretty heavy, in the range of multiple hundreds of megabytes for a simple hello world. That's an issue because each time you need to run that container, the container engine needs to fetch that container image from a registry that is hopefully co-located on the same network. But still, to run some very basic application, you still need to fetch multiple hundreds of megabytes. So that's an issue. So we need to work on that. So when it comes to containers, we tend to talk about latency. Latency is basically the time it takes to send the result to the users. And we can split that in two. So there is the time it takes to start up the containers, and then there's the time it takes to start your application, in this case, the Java virtual machine, within the containers. So if we look at the first layer, the container startup, we need to keep in mind that a container is basically made of layers. So we have multiple layers on top of each other that compose our container image. The idea here is to have as small as possible layers. When it comes to GVM container image, we have 3 types of layers, top to bottom. So at the top, we have the Java code, or the byte code anyway, with all its dependency. Then we have, under that, the Java runtime layer. That's the Java virtual machine and something else. And then under that, we have the operating system layer. And the basic idea is basically to shrink those layers as much as we can. On the Java application layer, there's not much that we can do. I mean, there's not much that the GVM can do. We can only give you advice, like watch out for the dependency that you are using. Don't make sure that you are not embedding the whole world with transitive dependency in your code. So it's really just best practices. The thing that you need to do is try to leverage the cache mechanism that we have with containers. That's why it's a good idea to keep everything which is relatively static in different layers. And that's why maybe fat-jar are not a good idea when it comes to containers. But that's up for discussion for another session. The thing that the GVM provides is CDS. That's something that you want to leverage. And we're going to discuss CDS later on. So moving down, at the Java runtime layer, there's something that we can use to shrink the size of that layer. And that is Jlink. So Jlink is a tool that has been added in Java 9. And basically, Jlink gives you the ability to create your own custom runtime. And your code doesn't have to be modular for that. You can take an existing Java application and run it on top of a custom runtime created by Jlink. To give you an idea of the benefit that we can get using Jlink, I took JDK 13, OpenJDK. I started with a full JDK that weighs over 300 megabytes. Then you want to create just a runtime. That's also a good idea within the container space. From a security standpoint, it's a good idea to reduce the potential surface attack of your containers. So that's why when you're running your code, you don't need, for example, to have Java-C or JMap, all those tools in your containers. They're not needed at runtime, so just get rid of them. So we want to use a Java runtime instead of a full JDK. So with Jlink, we have the ability to create that runtime, that custom runtime. So all the modules, so that's basically a Java runtime that includes all the modules, 168 megabytes. Now, this is very stupid to create such a runtime because there is no way any sensible application can make use of all the modules of the platform. That's what I'm doing next. I'm creating a Java runtime with just the modules that are needed by my code. In this case, this is a serverless Java function. From 168, I go down to 50 megabytes. And then Jlink comes with a few additional flags that we can use, like we have the ability to remove the header file, the man page, and so on and so on. If we do that, we go from 50 to 44 megabytes. And Jlink also provides two levels of compression. Compression 2 being zip deflate. So if we do that, we go from 44 megabytes to 34 megabytes. So basically, 34 megabytes, I have a custom Java runtime that includes all the modules and just the modules that are needed by my code. So that will greatly reduce the size of that layers. The thing that we have to keep in mind is that if you look at the bottom, I've used compression just to reduce the size of that layers. Now, compression means decompression. So maybe it's not a good idea to use compression if we want to save some time, because at runtime, that would imply some decompression cost. Maybe I should have stopped at 44 megabytes. That's something that ideally you should measure. Moving on, at the operating system layer, the GVM cannot do much. You should use optimized distribution. So slim distro, for example. Now, it's not because there's slim in the title of the distribution that it's really slim. Check that. There's the distroless distro from Google. It weighs almost 200 megabytes. It's a bit heavy, but it has a Java. The thing is that it's Java 11 only. So it has some limitation. And then there are tools, such as Docker Slim, that in my case doesn't work, so I will not comment about that one. We can go further than that. We can use super optimized Linux distributions such as Alpine. So Alpine is an optimized distribution that weighs between 5 and 6 megabytes, depending on the version. And it's basically a complete Linux distribution to run your code. Obviously, with that size, you don't have all the bell and whistle that you have in a typical Linux distribution. But again, from a container standpoint, we want to reduce as much as we can the potential surface attacks. So it's good to remove all those bell and whistles that are not needed anyway. The thing is that Alpine rely on muscles, muscle being the C library that the C++ code is using to talk to the kernel, to the Linux kernel. OpenJDK is using libc. So OpenJDK is using a different libc to talk to the underlying kernel. So you have two options to basically run OpenJDK on top of Alpine. Either you rely on Alpine package glibc, which is basically an intermediation layer that will, whenever there is a libc call, it will turn that into a muscle call. I'm not sure it's the right approach. Or you can use Project Portola. So Project Portola basically compiles OpenJDK on top of muscle. So you can use OpenJDK on top of Alpine. The thing with Portola is that, so today, the current release of Java is Java 13, so we already released Portola builds for 14. Why? Because Portola doesn't go through all the testing that we usually do on OpenJDK, so you can use it, but, well, pay some attention. Having said that, we are always looking for helps to help us maintain that build. So if you're willing to help us, you're more than welcome. So I'm going to demo that. So I'm not sure anybody got that joke. It's demo. No? So its demo is basically a retail chain in Japan. Yeah, I'm pretty sure it wouldn't work here. So what I'm going to show you now is basically Jlink with Alpines. For that, I'm using a server. I'm using the Minecraft server because it was open source. So what I'm going to do, so let's see. So what I have here, server.jar, is the Minecraft server from Microsoft, and some of the files that are needed by that server, like the ULA.txt. If it's not there, it won't start. The server properties, and so on and so on. I have a Dockerfile to containerize that guy. So it's a multi-stage build. So the first build, basically, I'm taking 14 Alpine. And then I'm using Jlink here to create a custom runtime. Compress2 to compress everything as much as I can. And then I just need to specify which modules are needed by the Minecraft server. And it turned out that the Minecraft server needs those 12 modules. There is a specific tool that you can use to figure out which modules are needed by your code. And then the second stage is basically from a pure Alpine distribution. I copy all the files. So those are the Minecraft server files. And I'm also copying from the previous stage the custom runtime. And then I just run that guy. So docker build -t mine. Nope. Let's see if it's here. Well, sorry, my laptop just crashed before. So starting, let's see. If I don't have the OL, sorry, I'm going to have to, well, no, let's start Docker. And I'm going to come back to this one because starting Docker locally can take some time. So yeah, Docker is starting. So remind me that I need to go back to that demo. But anyway, I have the result here. So using OpenJDK, so the OpenJDK 13 distribution from the OpenJDK community, so the one that is using Oracle Linux, the 12 modules weight 88 megabytes. If I strip debug, so basically if I remove the debug information out of that custom runtime, I would say 14 megabytes. If I compress one, from 88 megabytes, I will go down, I would save another 18 megabytes. And compress 2, I would save 31 megabytes from those 88 megabytes. If I remove the header file and the man page, I won't save anything because in that particular distribution, they are not included by default. So something important. On top, you have the OpenJDK 13, a custom OpenJDK 13 with one modules. OpenJDK 13, so from the build that are done by Oracle, it weighs, let's say, 15 megabytes. Then at the bottom, the same custom runtime image, one modules, using the Debian OpenJDK 13 build. It weighs nearly 500 megabytes. So about 10 times the size for the same exact custom runtime. Why? Because the Debian ones is embedding the debug symbols. So if you are, if you are concerned about the size of your Java runtime layer, you need to clearly remove those symbols. In Java 13, we have added these new capabilities to Jlink, strip native debug symbols that you can use to basically remove those symbols. If you do that, you will go from 499 megabytes to 15.1 megabytes. That's something that you should clearly look at. So latency. Let's see if Docker has started. Yes, it looks it's there. So I'm building my Minecraft server. Let's look at the size of that image. So that Minecraft server, the container, weighs 100 megabytes. We can look at what's inside. Dive, mine. So those are the different layers. So the first layer is the operating system layers. Then this one is basically just creating a directory. The second layers just had this small text file. This one had a property file. Maybe it would have been a good idea to combine all of those together, but it's not the point here. Then we're adding the server.jar, which is the Minecraft server. Well, I'm not sure how. Oops, sorry. So that guy, wait, I think. Okay, that guy, wait 36 megabytes. So the Minecraft server itself is already 36 megabytes. And then the next layer is basically the custom Java runtime. If we look at the size of that, 58 megabytes in that case. That's basically what I had with compression 2 before. So clearly, 100 megabytes, we have the operating system, Alpine, we have the custom Java runtime, and we have our application that in this particular case already weight 36 megabytes. So that's something that you should clearly look at. Okay, we've discussed how on the Java side you can improve the startup time of the container. The next step is basically to look at the Java startup time itself. So this slide shows the startup time between Java 8 and 9. And clearly it's not on my slide, but smaller is better. So we had a big regression between 8 and 9. That's the bad news. The good news is that it has been fixed. So you see on the right side, the startup time. This is for a simple Hello World application. In JDK 14 that will be released in 2 weeks has been improved versus 13. I can tell you that in 15 we will be able to shave another extra milliseconds. This is something which is very important in the container space when you are using ephemeral containers. So basically containers that will be invoked, will perform their task, and will die shortly. Then the startup time of the application is something which is becoming important. This is the same slide, but with additional data like Hello World using lambdas, Hello World using concat strings. So basically the takeaway is that if possible, you should look at the recent version of the JVM if the startup time is something which is important to you. Something else that we can use is CDS. So the previous example were quite visible because we just had the startup time of the application, and the application was very trivial. CDS is something that we can use for non-trivial applications. So anybody knows what CDS is? Class data sharing? Okay, 2 hands, which is very low because CDS is not a new capability. CDS is in the platform since Java 5. So the basic idea with CDS is the following. When you run a Java application, the JVM will load the bytecode from disk, and it will have to perform a bunch of operations before it has something that the JVM can use from the memory. With CDS, the JVM will perform that, and once it has the in-memory representation of your bytecode, it will dump that to disk. So that the next time you use your application, the JVM will directly bring that into memory. So that it doesn't have to go through all the operations, which are expensive, and the thing is that obviously you have a lot of classes. So that's the basic idea with CDS. In the early days, CDS was quite limited, so CDS for Java C5 was just for the runtime classes, so the RT.jar back then. It was limited, I think, to serial GC and so on. But basically, all those limitations have been lifted since then. So let's have a quick CDS demo. So for that, I'm going to go back to my Linux box. So I'm going to compile that Hello World application. Java Hello World. I'm going to time that invocation, time Hello World, so 115 something milliseconds. To get some more accurate number, I'm going to invoke that application many times without and with CDS. So for that, I have a nice tool which will invoke the application 42 times per 42. And for the first run, I'm going to disable a CDS. So to disable CDS, I need to use that flag. So the application is invoked 42 times, and on average, it takes 200 and something, 220 milliseconds. Now I'm going to use CDS. So I'm going to do 42 invocation, but with CDS. To use CDS, well, it's pretty easy. Just remove that guy, because now CDS is enabled by default. So 222 versus 157. So basically, this time we're at 71% of the startup time than the startup time without CDS. And that's something that you get for free. It's in the platform. Now, the thing that you might say, OK, this is good. I mean, it's a huge win. But it was a trivial application. This tweet is coming from the gRuby project lead. So he works at Red Hat. And basically, the number that they have now with JDK 14 using app CDS, just look at the bottom. So JDK 8.202, 853 milliseconds. Now with JDK 13, 717 milliseconds. So the gap is quite important. And gRuby is not a trivial application. It's really a complex application. So again, in containers, when startup time is important, that's something that you should consider using CDS. Application CDS is basically the ability that CDS gives you to dump all your classes of your own code. So your own application, you can create an archive for CDS. So CDS introduced in Java 5. It has been open source in, I think, in 10 with application CDS. Well, in Java 9, it was a commercial feature anyway, so yes, it has been open source in 10. And we're keeping to improve CDS. So for example, in 13, we have added dynamic CDS, which gives the ability to create the archive of your classes when your application exits. So basically, you run your application once, and at the end, when it exits, it will create an archive with all the classes. You can go further than that. If the startup time and the footprint is important. You can look at GraalVM. So GraalVM is a project run by Oracle Labs. It's an high-performance polyglot virtual machine that provides many capabilities. On the Java side, there's this polyglot API that you can use to interact with different language. They have a JIT compiler, which is written in Java. So it's a JIT compiler that you can use to plug and replace C2 within hotspot. The nice thing about that is that the JIT is written in Java, the JIT compiler is written in Java, and it's quite it's very performant. And then they have these native image capabilities, which basically allows you to take some Java application, so some bytecode, and turn that into a native executable for a given platform. So let's have a look at GraalVM. So now I need to find the right machine. So this is this one. So Java, hello world. Oops, sorry. This is the application that we're going to. So first I compile the application, and then I'm using this native image tool from Graal to compile it, to AOT compile it. So it takes a bit of time. So let's have a look quickly at what is done behind the scenes. So basically what I give to native image is a jar. That, well, not a jar in this case, it's a simple class for my application. So I'm giving it an application. It will go through this native image tool that will scan the code to find all the potential execution paths. And then it will remove all the dead branches. And once it has that, it will turn that code into native code, so machine code that will run on a given platform. In this case, it's a Mac platform, so I will have, in terms of output, a Mac executable. And let's see, it's done. So it took like 42 seconds. If we look here, we have this hello world file. If we look at the type of that file, it's a macOS 64-bit executable that I can obviously invoke. So, well, you see the startup time is pretty fast. So 13 milliseconds, that's pretty fast. If we look at the size of that executable, 8 megabytes, that's the only thing I need. I mean, there's no external Java runtime that is needed. So if I compare that to pure Java, so for that, I'm going to switch to a different version of Java. So Java, so let's first compile the class with that version, snobs. Java hello world. Let's time that. You see 143 milliseconds. You see that the Java version is different, so this is Java 14. Now, to be fair with you, I have a bunch of JDK installed on my machine, so that has a bit of time. So if I want to get more accurate result, I need to invoke directly the right JDK, assuming I can find the JDK 14, RC1, home, bin, Java, hello world, and I need to time that. So I was at 145 milliseconds, and this time I'm at 800. That's weird. Okay, 93. 93. 83. I can go down to, no, but that's a more accurate number. But still, we don't have the performance in terms of startup time that we have with Graal. That's clearly. Why? Because here we have a full-blown GVM. We have hotspot with all the capabilities of hotspot. So, that's Graal VM, native image capabilities. There are a few limitations. So it only supports Java 8 and 11. There are also some limitations. Mostly supported basically mean that it works, but you need to configure that, like the use of a GNI, for example. And then there are a few things that are not supported. The thing is that what you will get in terms of output is a native executable. So you lose the portability of Java. You don't have a jar. You have a native executable. So that's something that you have to keep in mind. You will also lose the ability to use some of the tooling that you might have on the Java side, like for managing or observing your application. GMX, those kind of things might not be available. So that's something that you have to keep in mind. But still, if the startup time is something important, you need to look at Graal VM native image. The thing also with Graal VM native image is that the footprint, so the memory footprint will be lower. Something that Graal doesn't have is, for example, the GC and G1, even though they have a G1 GC, well, they have a low latency G1 based GC that has been introduced. I'm not sure it's a full features yet, but clearly they don't have all the capabilities that we have with hotspots in terms of GC, for example. Talking about GC, in 14 we have improved G1 GC with NUMA capabilities. So NUMA stands for non-uniform memory access. It basically means that your memory is not always equidistant to the CPU. So it's a good idea for when you access something in memory that your code is aware of that. So the GVM, basically, the GC is now able to deal with NUMA architecture. Something else that is not clearly advertised is all the improvement that we're doing into the platform. Between Java 8 and 14, there are over 700 enhancements that have been done just for G1. Altogether, they are bringing extra new capabilities. So just one that I show on this slide is the memory footprint of G1 for a native heap, in this case, of 16 megabytes. So the extra overhead in JDK 8 for a 16 gigabyte heap was 4 gigabytes of extra memory. In 11, we were just below 3. And in 14, we are below 2. So basically, between 8 and 14, we have dropped by 2 the extra footprint needed to deal with a 16 gigabyte heap. Not only that, we have also increased the performance of G1. So those are the kind of features that are not advertised, but that you need to keep in mind when looking at a new version of Java. And that's something which is also important when your GVM runs into containers. The footprint is obviously very key. So let's talk about security. You might have seen this tweet that says that the top 10 most popular Docker containers each contain at least 30 vulnerabilities. The good news, Java is not there. So that's the good news. The bad news is that we're not immune. This is something that popped up on the OpenJDK mailing list. And basically, someone realized that in that case, that was Debian. They released 11-something GA release even before it was officially GA. I mean, the source code is there, so anyone can build from the source code and claim it's GA. So watch out. 2 weeks ago, I saw that. So someone was looking for OpenJDK 11 GA Linux build for muscles. The thing is that there's no such GA build. Nevertheless, someone figured that if you take that particular build, you can consider it as the OpenJDK 11 Alpine general availability release, even though that release doesn't exist. So, and then you look at the Dockerfile, and well, it's maybe very small, but basically the Dockerfile is doing a wget from a file coming from a university in Austria over HCP. The good news is that they are checking the SHA-256 checksum, but from the same source over HCP. So, and it's on the internet, so it should be true. So then other projects were using that as the 11 GA Linux. I mean, so my advice here, when it comes to Java, but also container in general, you should choose your base image wisely. Not only that, you should secure it. And you shouldn't trust someone else to do it. And don't believe what you read on the internet. So, there's these new trends where it's a good idea to run rootless containers. So basically, we want to give as less privilege to the container as we can. It's a bit tricky to do. Docker, they have a rootless mode, and last time I checked, it was still an experimental features. If you want to do pure rootless container, you need to use Podman. For that, Podman use cgroups v2, which is not something new. I mean, cgroups v2 have been added in kernel, in the Linux kernel in, 6 years ago. But it was not enabled by default. It's now enabled by default on Fedora. So Fedora is the first major distribution that enables cgroups v2 support by default. So with that, you can easily do rootless container. But on the JDK side, you need JDK 15. So JDK 15, we had support for cgroups v2. I put a little asterisk. Remember the first slide, the disclaimer slide, that basically says that it's there the day it's there, but that's really the idea. So JDK 15 will support cgroups v2, and if cgroups v2 are not supported on the platform, it will automatically fall back to cgroups v1 as today, right? And then, in terms of security, it's just common sense. So choose your base image wisely, and the rest is just pure containers. So watch out at the certificates that you have in your container image. There are a bunch of security offering of tools that you can use to basically scan your image for vulnerabilities, and so on and so on. And also, it's containers. So the basic idea, you should try to reduce as much as you can the potential surface attacks. On the Java side, we have Jlink that is useful to achieve that. OK, let's quickly talk about observability. So the JDK comes with a bunch of tools, GCMD, Ginfo, GPS, Gmaps, and so on. The thing that we tend to forget is that we can also use them either on the host. To do that, obviously, the host needs to have privileged access, so it's not necessarily a good idea. But you can also run them within the containers, like doing a Docker exec, and then the name of the container, and then, for example, Ginfo. And doing that, you can get useful information about the JVM that is running inside your container without having to do anything else. So that's something that you should try to leverage. Something else that is coming in the JDK since 11 is JDK Flight Recorder. So GFR is basically a black box that is built into the JVM. So the JVM is emitting event. It's very low overhead, so that's something that you can use in production. And then you have the ability to analyze those events. Until now, those events, the analysis of those events were basically done post-mortem or after the fact. So you start the recording, you stop the recording, you dump the recording, and then you do the analysis. In JDK 14, we have the ability to stream the event as they happened. So you can analyze the event in process. Doesn't really make sense in this case, but you can also analyze the event outside of the process. So what you can have is you have your container that is using GFR. It's low overhead, so that's something that you can have on all the time. And for example, the repository is basically where the events are being put, can be in the volumes that you can access from a different containers or from the host, those kind of things. So that means that you can now start to think about scenarios that are using GFR to basically emit events from the JVM that is running within the containers and consume them outside. That's something which is new in JDK 14. So, wrap up. JVM in containers. The JVM needs to behave as a good container citizen. So the advice here is you need to use a recent version of the JVM. Don't rely on an old version of the JVM like I did at the beginning. Then I've discussed quickly some tricks and tools that we can use to reduce the latency. That's something which is important in the container space, keeping in mind that there are two types of latency. First, container latency, so the time it takes to start the container, and then the Java application latency. And then something which is important is that all the other investment that we're doing into OpenJDK are also leaking into containers. So if I take, for example, Loom, Panama, ZGC, all those features which are not by design conceived for containers will also work nicely when they are being deployed into containers. So that's also something that you need to look at over time. So JVM in containers, choose your base image wisely, secure it, use the latest Java version, and never use Java latest that base image. We're trying to get rid of that one, but it's very difficult. That's only something that you can use on stage when you're doing demo and you want to clearly make a point to not use it. Only rely on actively supported version. They are all container aware, so JVM Ergonomics will kick in. There is this flag that I often see, use container support. Those days, you don't need to use that flag anymore because the JVM is by default using the container support. So you should only use that flag if you explicitly want to disable the container support, assuming you have a valid reason. And then don't use a full JDK, but try to use a GRE or a custom Java runtime for your code that is running into containers. And with that, please stay safe. And we have 3 minutes for questions. So are there any questions, remarks, comments, jokes?
Hi, David. First of all, thanks for the talk. That was a real tour de force, and I was really happy to see that you went back to talk about Alpine and the fact that actually it does come from this weird unsupported place, especially for 8 and 11. I had a question about Graal. So you mentioned that one of Graal VM's limitations is invoke dynamic. Like all of Invoke Dynamic?
No. So it's just a copy and paste from their site. Invoke Dynamics works, but there's something that I didn't really check. Right. So that's a copy and paste from the GitHub page from Graal, but no. But I want to make sure that I use the right limitation that they are saying.
So lambdas work?
Yeah. There was a question, just someone, yes.
Okay, I think we basically got time for this one question, and then I think we'll have to call it a day there.
And just for info,
I can't run through the audience.
Just for info, Ben is the one with the very long safe harbor statement slide.
Hello.
Hi.
I just wanted to ask you about the thing that you mentioned with all the official supported JVMs being container aware. Is that valid from Java 8 onwards for all of them?
So the question is Java 8 supported into containers?
As in container aware?
Yes. I believe it's starting from 8.199. Mm-hmm. So my advice, if you are using Java 8, use the latest version of Java 8. But since the container support has been added in, I think, 1.99. So yes, if you use a recent version of 8, you're on the good side. Having said that, it's a good idea also to look at 11 and more for just the extra features that are provided.
Sure. I was just wondering if you still need to use the 2 flags, experimental VM options and the C group, something.
No, those have been removed, but you need to look if it's in 199 or in 210. But those flags are removed.
Yeah, okay, thank you.
So the container support is by default.
Okay, so thank you very much, David.